A very welcome to my ASM school for Amiga. This is Photon of ScoopX. I hear a few guys at least have discovered my ASM school and appreciate it, so that's always nice to hear. Let's continue the tutorial, and I'll try to talk a bit slower in order for my Anglophile pronunciation to be a little bit more correct. It could be that I'm nervous as well, I guess. But I think slower will do it. So, we were here. Whoops. And I accidentally the source. And we discovered that by copying the value from a register to another, we could modify, we could add a thickness to the line, or the bar, as it is now. No longer a line, it's a bar. And this is as far as we've come as yet. Now, I addressed some things in tutorial 6 which were left unexplained, and one of them touches on a concept that could be new to people coming from other platforms, usually PC, because PC is one of the few platforms that have reverse byte and word and long word ordering of data in memory as compared to other platforms then. Usually it's not of any concern to a high-level language programmer, but I'm assuming that you want to learn assembler in order to learn how a computer really works, and it can work two ways when it accesses memory. It can either store them as they should be stored, or in the logical way, which is the most significant bit first and the next most significant bit and so on, so that the memory becomes just a big bitmap of bytes, words, or long words, and it doesn't matter in which order they are arranged. And the bits go from most significant to least significant all the time, and changing a variable from byte to word to long word doesn't reorder the bytes and words within a long word, for example. Now, this may not mean anything to you, because I've not showed you what anything looks like in memory yet, and that's what the monitor is for. It's up here in the menu, but you can also type H and a random address. For example, if you remember, a label signifies an address. It's just a symbol which you can print out the value of like this. So here are all our labels in the program, and they correspond to addresses in memory. Now, this is not an absolute addressed program. What that means is that you will get just offsets here, so that init, the first label in the program, has offset 0, and exit has an offset of hex 92. And here's where memory addresses come in. If we absolute address this program, what we have now is the same as putting the code, I guess, I don't know how the assembler will react, putting it in a section. And a section statement has two arguments. The first is some sort of hunk name. Programs in the Amiga are stored in a, I guess, Unix, Linux type header way, which divides them into hunks so that the operating system can relocate them to whatever free memory is available. We're going to do the opposite of this now in this exercise, just to get some absolute addresses out and examine them in memory. So I'm going to call this tutorial. You can't have too many characters in there. I think 16, maybe 12, 8. I have no idea. All my sections are named SCX for some reason. And you tell it if it's data, code, or BSS. Those are the usual hunk types, apart from photon, which is also a hunk type. Either way, this is code, and you can specify, you can hardwire or direct which type of memory you want this hunk to be relocated to. And this is special to Amiga, of course, because it's one of the few platforms that have different types of memory. Chip mem, and essentially, well, you have two types. You have chip memory, which is memory shared with the custom chips, so that all memory accesses from the CPU, from this code, is competing with direct memory access, or hardware DMA, which, among other things, displays sprites and reads the bit planes, the screen data from memory, and sends it to the video output unit. So that's the chip memory, and the other type is fast memory. The only thing this really means on Amiga is when you say fast memory, you mean not chip memory. That's all you mean. And if the user doesn't have any fast memory in his, for example, in his Amiga 1000 or unexpanded A500, A600, or A1200 computer, then the code can't run. It will say not enough memory available when you try to run it. So hard coding it is generally a bad thing. Sometimes you have to do it. For example, custom chip data needs to be in chip memory, and this is why we have this section here. So maybe I have a short memory and I've explained some of this before. However, we can specify that either that this is code but the memory type doesn't matter, or that we specifically want the fastest possible memory in the computer, like this. And as you saw before, the _C means chip memory, and _P is public memory, but that's the same as not specifying it at all. Then it takes whatever memory is available, usually fast mem, if that's available, and then chip memory. So that if we put this in a section, and right, I can't name them the same thing, I'll have to call this tutorial data, and we check the symbols now, and they're still relative, as you can see here. The opposite of this is, let's say we put all of this in chip memory. I like to do this because it's a convenient way to code Amiga OCS, ECS demos. On these computers, you know that you have at least 512K chip memory, some of which are eaten up by the operating system, but at least that's the part where you can put all your code and data in. And then if you need some storage or buffers or stuff that's not used directly, that is, the copper list is run directly, the code is run directly, so it can't be in the wrong place, so to speak. But, and I will calm down again because I'm trying to explain everything at once. But it's a good model just to put everything in chip memory and use the fast memory as an optional memory for large tables or large buffers, that decrunch buffers or what have you. that's an excellent way to keep compatibility with the old platforms. So on this setup that I have here in Win UAE, I have an original Amiga 500 configuration with half a meg of extra fake fast RAM. It's so called because it's a cheap expansion that isn't really faster than chip memory, but just a way to get some more memory cheaply. In other words, it has none of the advantages of, for example, functioning as a DMA buffer for a hard disk interface. Again, I get sidetracked. Anyway, just explaining why I call it fake fast mem. It's the usual term for it. Now, how do we get the symbols out that are absolutely addressed so that we can see? Well, the easiest way is just, whoops, I have to put an even here. Well, that's a good work. Yes, as you can see, the default section that you don't have to type out in the header is to public memory, and it takes fast memory first, so the copper ended up in fast memory, and the copper chip can display copper list in fast memory. So if we have a section here, put everything in chip memory, we can just print the value of init and see that where it actually ended up in memory was very low down at address ABD8. That's in the first 64K of memory. But perhaps that's not good enough. Perhaps we need to have more control over where our program ends up. It's a cheap and dirty way to get things started, and I should say operating system unfriendly way to get started working with memory. So this introduces the org statement. Means organize. You can organize a program to hex 20,000 if that memory is available. We'll check that in a moment. And you can load it to that address. However, if you make parts for a track-loaded demo, for example, you might want to organize it to a different address and still for testing purposes load it to a higher address, because that memory is not available when the operating system is loaded, but it is available from a boot track loader point of view. But for now, the usual way is to org it to the same address as you load it, and this will make this label have the address hex 20,000, which is the start of the, which is 128K into chip memory. So that means in order to build a mental memory map of where to put your stuff in your demo so that you know that it will run on all the Amigas, you can try this exercise. I have in my startup sequence a command made by me. It's a command line command called chipmap. It's available at scoopex1988.org. And it tells me that these areas are free and the address ranges in between them are occupied by operating system data and also, of course, the ASM1 program. This means that from hex 15F90 and up, we can use whatever we want, as long as we don't start, starting a module player or start ProTracker or Deluxe Paint or whatever, because then we will have to type the command again to see if we can run our program. Now, this is just an exercise to get acquainted with the memory in the Amiga, and is not recommended. The recommended way is to allocate everything you need and not rely on any memory to be free at a certain time. However, when you start pushing the boundaries, then you need all the memory, and then you'll just have to assume you have all the memory. And should someone have a DF1 floppy drive connected, eating 22K extra memory, then you will ask that person to please disconnect the drive in order to be able to run the demo and return to the command line interface, that is. This is all very new to you if you're not acquainted with how demos are run. Usually this is a domain for old fogies like myself and competition organizers. So now we have put our program and our data starting at hex 20,000. That means that we know that memory is free. So that means when we assemble the code into data, into binary code in memory, it will occupy those addresses and upwards, and will not overwrite anything like the ASM1 screen memory or something like that. That can happen if you put the org and load addresses too low in chip memory. So now when we type the symbol table, we should get absolute addresses, and this is why this is good. You will in some ASM1 versions and also some other assemblers get relative mode error if you use if you want to calculate, for example, the size of the code in our program. That's the advantage of doing this, and it's usually not a problem if you keep a close check on your startup sequence and have a dedicated startup for the Windows emulator, or for the Amiga emulator, or for your real Amiga. So by using this, we know that our program is 146 bytes long. We can use the monitor from this address, or if you prefer a space in between, to see what our opcodes, as they're called, what our instructions have been translated to in binary. There are some opcodes that are recognizable. Usually you would want to examine words when looking at code, in the binary form, I should say. Because no instruction on Amiga is 1 byte or 3 bytes long. They're all divisible by 2, which is why it's pretty hard. It's a bit harder to code size very small demos on Amiga than say 8-bit computers or PC DOS, the PC DOS environment. So this doesn't tell us very much. We may recognize some of the commands in the carper list. See where we have them. They're down here. We have await here, and background color change, and so on. But that's no surprise, because we declared these words in memory. So naturally they end up there. But the assembler job is to translate our human-readable code into machine-readable code for the CPU. And this is what we end up with. So here's an opcode that some of you might recognize. That's an RTS, the RTS statement, just before the text string here. So this is the 4E75 hex code that this instruction got translated into. These constants here are translated to hex C000, followed by some, preceded by some word hex instruction, and so on. The point of showing you the monitor was to get into variable sizes and how to verify that poking a copper list actually pokes in the right place and pokes the right values. For example, if we run this, here's another vital thing. In some assembler versions, The command might be called something else, but you want a jump pointer because the J command otherwise would need jinit to work. With a jump pointer, it jumps to the init. So here's our program, and if we stop it somewhere near the bottom, we should have a high value in the corpus list, and we know that we poked the value into wait ras 1 labels and wait ras 2 labels. Right here. So if we want to check the entire command here, that's 2 words. That's called a long word, and a word is 2 bytes. So these are essentially 4 bytes in memory. First hex 80, then hex 07, then hex FF, then hex FE, or a long word of hex 8007 FFFE, or 2 words 8007 FFFE. So we can look at this position in 3 ways. We can unspecified, it defaults to bytes. So if we look at wait ras 1, we should have a quite high value, somewhere maybe around hex E8 in the first byte. D8, well, close enough. And we didn't change the other 3 bytes in this wait statement, so that they are 07 FFFE as declared in the source. We can examine it as words, and then it looks more like a corpus list, and we can examine it as long words, like this. I prefer this to look at corpus lists this way, because each corpus list command is a long word, so it's easier to read. Now this is just for debugging purposes, of course. Normally you never need to check memory. You might want to maybe hack into some structure from some program, and then you'd use this to examine the memory. If you want to look at code, you can use a disassembler-like resource, or you can use the disassembly command or insert disassembly command, which will insert whatever range of memory you want disassembled into your source, and it will ask you if you want to remove some unused labels and so on. I won't demonstrate this here, you can experiment with it. But if we disassemble from init, we should see our init code, and to the left here you see the corresponding binary or hex equivalents in memory. We can see from this that this instruction takes 2 words in memory. This instruction takes very little memory, in fact the minimum of any instruction, 1 word. Normally these are not very important, but if you want to check that your code got assembled right, or check that your code didn't get overwritten by some rogue routine running going bananas, then you can use this disassembly command. So this is actually the debugger window now, and we can use this to an extent this time, because we turn off the interrupts near the very start here. So we can debug it down to here, down to but not including this instruction, and then we'd have to bail out. Now I know that this ASM1 1.20 usually doesn't work with the debugger in the Windows emulator, but we could give it a go, I guess. You could press Amiga Shift D or Control Shift D, or press type AD, assemble debug. Let's see if it works. Nope. So you can try some other versions. I've made a very early version a long time ago, which is ASM1 version 1.02 plus, which is 1.02e by Promax, with just a few conveniences and bug fixes. It's very light on the memory, but of course if you need support for all kinds of CPUs, then go with this one. If the earlier versions of ASM1 also have an emulation bug, namely that when you press escape like this, it doesn't move the cursor correctly. There is some, I think, ANSI control code there that doesn't get executed correctly. So therefore that's why I'm using this in the emulator that I'm recording from. Enough talk, let's fight. So this is a lot of talk just to show you what this means, and this is the follow-up, namely that, as you can see here, we have .l. What that means is this move command gets tweaked to another little command, which is move long word. So it takes a long word from this address, and the .w signifies that the address specified is a 16-bit address in the very first 64K of memory where exec base resides and the interrupt vectors and other important addresses. That's just to save 2 bytes. We can check that. If we remove that, we can check it first. Assemble. We can see that this instruction takes 4 bytes in memory, 2 words. If we remove this, it instead takes 6 bytes in memory. So it's just to save 2 bytes of memory. It's a habit. So this has nothing to do with the size of the instruction. I should say the size of what the instruction is addressing, what the instruction is moving or clearing or modifying in some way. That size is specified here. That's the size of the data that the instruction manipulates. Likewise, here we want to clear the whole data registers. The registers in the CPU are 32-bit. That means they are 4 bytes. They can be addressed either as byte, word, or long word. If you are changing this to a byte, you're only clearing the lowest byte in that data register. That is, the other bits 8 to 31 are not affected then by this instruction. Likewise, if you clear only the word, then only the lower word in the data register is cleared. Bits 16 to 31 are not affected, but this clears the whole register. So and going through the source once again, some instructions don't require a size. A jump to a subroutine, for example, is always the size of this is specified by the so-called addressing mode. So this is a jump relative to an address register. This is also a jump relative to an address register. This is a jump relative to the program counter, where the CPU is right now. In other words, on this line. When it's coming to this line in the program, then without going into further details, it's simply the case that some instructions don't require sizes. However, there's an optimization feature here. Let's see if we can optimize this program. Normally, if you specify nothing as size for an instruction, as for these moves up here, then you mean move.word. I myself prefer to spell it out for all my commands. You can choose this as you want, but I often see silly things like move q dot byte That's a move quick command for an 8-bit value, signed value, to a register like this. We're not going to use this now, but this is simply wrong. Some assemblers allow it. MoveQ has no size, but it can have only one size, and that's long word. This would a 0 here would clear the whole register. But here, as you can see, changing that to it needs to be word size, so we haven't optimized anything by adding the unnecessary .w, which is the default size for 68,000 instructions. We've only spelled it out, so that when we look at this code again, there's no doubt that we're changing only the low word of data register 7 here, for example. We can use this new gain knowledge by optimizing this. If we disassemble this instruction will take 4 bytes. Let's try it. As you can see, since I've specified the jump pointer, I don't have to specify dinit now that I have that jump pointer. So if we scroll down to this, we set the add value to 1 here, and it takes 4 bytes, as you can see, 2 words. And if we want to preserve the high word of this register, that's the correct way to do it. However, we know that's not important right now, so we can change it to a move quick version. And it's 2 cycles faster because it doesn't read the hex 0001 from the code in memory. So it's faster, and it also takes 2 bytes less because it fits the constant in with the other opcode. Let's try it. So for the move Q here, this is the instruction we change, and we see that it now only takes 2 bytes. We can't do this for this, however, because it's higher than 127, so it doesn't fit within the move Q command. If you change this, you will get illegal size or something, out of range 8-bit. And that's because it's a signed 8-bit value, so only values between -128 and positive 127 can be used with move Q. Let's move on. We wanted to optimize the branches. We have an opportunity here to save 2 cycles and 2 bytes by specifying a byte size here, and that's possible because the distance from here to here is only something like 6 bytes. And it's possible here also because we don't have many bytes of code here either, and essentially so on. So the quick way to do this is to use assemble optimize. This will only optimize branches, and it will have changed all these to byte sizes automatically, and they all fit within the signed 8-bit jump distance. Otherwise we would have gotten a reassembly. It would change it towards the out of range branch to word size and then reassembled. So now we can check if we have less than 146 bytes of code. Yes, we've saved 14 bytes. Now, in manipulating and adding this vertical position for the bar, we have consistently used word size, and that's fine. However, we're poking just a byte here, so that in theory it would be possible to have all these be byte size, both for the direction register D6 and the position register D7. However, well, this would actually work, but you'd have to be careful anyway. So that's it. That's what I wanted to show you about um, another thing. The last thing I wanted to say about this was that the first point I made in this video was the ordering of bytes in memory. That means that a large value such as this address, when assembled, will be represented byte by byte in this order. This would not be the case if it came from PC, for example. Then it would be hex 80 F0 DF00 in memory. So this was just to address this difference. And that also means if you want to change a value in memory, you can make a little exercise of this. If you wanted to I'm trying to think of a good example. Well, I can't think of one right now. I think I will leave this as is, but as you can see, we haven't changed any code in any real way. It still works as it used to. But this was kind of a warm-up so that you know what to do in the next part, where we will turn on the bit planes and manipulate them so that we can get some graphics on our screen. And I might also append a quick exercise to turn this bar into a proper copper bar. I can leave that to the to the viewer actually, because it's a good exercise. What you do is you continue for each line. We can do this in this exercise. It's fun. Let's say we want to make a 5 pixel high copper bar, which looks like a metallic cylinder as seen from the side. In other words, not a boring white flat bar like this, but something like that looks more like a railing or something. We'll make this cyan, I believe, and we'll have to make 5 weights for this. Now a good coder wouldn't do this. He would make a loop, but you can practice that on your own. This is just to make a little example. So then the first position, if the first position were hex 80, the next would be 81. One down would be 82, 83, and 84. And we would increase the RGB values as we go towards the center of the bar, and then decrease them again as we go to the bottom. So let's do that. Let's not have boring white. And afterwards, we'd have to reset it to this background color. So let's do that. What's the RGB value for cyan? Well, we can start at the middle and set the maximum value F for 0 for red, F for green, and F for blue. These, I'll have to admonish a coder color warning here, but coder colors are good, man. We might decrease this by 1/3 so that this becomes 10, which is hex A, and this is 5. And likewise mirrored vertically like this and like this. Now if we run the code now, the code will still only change these two vertical positions, and that's not what we want. We want to change this, then we want to add one, change this, add one, change this, add one, change this, and so on. And I will show you how to make a loop, because I'm tired of copy pasting, man. And that's the advantage of copying it to another register. We have the original position, vertical position, in D0. So all we have to do now is we can essentially do it like this. We can do it before and do it like this. And we won't need this anymore. And we will repeat this 6 times, because as I showed you, we have 6 waits, because we need to reset the color to the background color down here. So let's do that. So we've copied, we're free from the counter, the global counter. We put it in a temporary variable here, D0, and we want to make a loop. We can use our newly discovered move Q command, and the way this works is you put the number of repetitions -1 in some register that you know is free. I know D1 is free, and then you put this is called a local variable, starts with a dot and can be used as many times as you want, as long as there is an absolute label in between. And this is handy because you don't want to type out, you know, poke copper loop 1, poke copper loop 2 if you do it somewhere else in the source, poke copper loop 3, and so on. You want the same label, and then you can reuse it. Like this. And don't use DBRA, the DBRA instruction. It's meaningless and obsolete, and it's the exact same thing as DBF. What it means is decrease D1 and branch as long as it's false, I think, or until it's false. Either way, it doesn't matter. This constitutes the loop, and we want to put our poke instruction inside it, like this. And we want to make this position dynamic, because otherwise we'd have to do it like this. And so we put that in an address register. And the way you do that, I will show you the pedagogical version and then show you what I think is the proper version. We need to initialize it, an address register with this address. So think for a minute, how would you do it? Well, you would move a long word, wouldn't you, into the address register, and it would be a constant like this. It would be like this instruction. You want to put an address, but you don't want to put it in a custom chip register. You want to put it in an address register. So basically you could use that. And we'd have to use an address register which is free. I happen to know that A0 is free. Basically, all the address registers from the start of the program are free, except A7, which is the same as the stack pointer, which is used to save variables, and we'll get into this later. So A through up to A6 is available, and I'll use A0. So this then points to the first byte of the first wait instruction. Another way is to load effective address, but then you have to remove this immediate sign here, and you might also want to make it PC relative. This will save 2 bytes. However, if your code is in fast memory and your copper list is in chip memory, then you can't use this. So since this is more easily readable, I'll keep that. So what we want to do is change this fixed address to this dynamic address, and then for each time we want to add some value to it, and we don't know that value until we examine the copy list in memory. So this is a good exercise. Oh, this is how you type it when you put something inside a memory address instead of putting it into the address register. You surround it with parentheses. Noob error. So we want to examine long word, let's say, or let's say we examine bytes, and we want to examine from that address and forward. So this is our first wait instruction, 8007 FFFE, changes the color, then we have 8107 FFE. So all you have to do is count the bytes. You can do that with the cursor key, well, sort of. 1, 2, 3, 4, 5, 6, 7, 8. So the offset to the next wait instruction is 8 bytes in memory. So we need to add 8 to the address register. But also we need to increase the vertical position by 1. We can do that now because this temporary work register is decoupled from the global global absolute position movement register. So that's it. Those who are proficient at assembler will already see some optimization possibilities here, but this should work. We'll write that down as tutorial 7. And let's look so we don't make a mistake, and then run it. Isn't that nice? A nice colored copper bar coded by a color coder. Nice.